Hello everyone, let's continue from the point that we left in the last video. So in the last video we applied a small gate potential at the gate terminal, and that actually repelled all the positive charges from this area into the substrate that left behind negative charges. So we see an accumulation of negative charges, and along with that, since this is a PN junction diodes, this behaves like a PN junction diode. You see a formation of the depletion region over here. And what does that mean? That means that whenever you apply a positive potential over here, this area starts to get depleted of its majority carriers, which is positively charged particles. Okay, so whenever in a PN junction diode, whenever you apply a reverse bias across the PN junction diode, there is a formation of depletion region that basically says that it is depleted of its majority carriers. In the same fashion, P substrate, which has got a majority carriers of positively charged particles, this area is getting depleted of its majority carriers. Okay, so next what we'll do is we'll try to increase the potential, but before that let's try to identify that this is the depletion region, which is very similar to the PN junction diode. Okay, so we'll increase the gate voltage and to a level, we'll increase the gate voltage to a level such that we try to see some phenomena. Let's try to increase the gate voltage. So you have to closely observe this area. So when you increase the gate voltage, we expect more and more positively charged particles to get repelled, and the depletion region width just increases at this area, because this portion of your P substrate, it's getting depleted of its majority charge carriers. Okay, so let's try to increase the gate voltage and observe this area of the gate. So we increase the gate voltage and you see the depletion region width getting increased. Okay, it gets further increased, and finally you reach at a point where this portion of the P substrate gets completely inverted into an N-type material. So out of this complete P substrate, there is a small region that gets converted into an N-type surface. Okay, this is called as surface inversion or strong inversion. This phenomenon is called as strong inversion, and the gate voltage, the VGS voltage at which the strong inversion happens, that voltage is referred to as threshold voltage. Okay, so the voltage at which your strong inversion happens, that's basically threshold voltage, and there are various parameters on which this threshold voltage depends on. So there is a whole equation, there's a long equation on threshold voltage. We'll come to that threshold voltage equation in some time from now, because that's the equation that will represent the MOSFET, and that equation will be used as a model for your SPICE simulation. So we have to come to the threshold voltage equations. For now, the potential or the voltage or the gate voltage at which the strong inversion happens, that is referred to as threshold voltage. So this small area of your P-type substrate, it's now no more P-type, it's an N-type material. Okay, this small area is an N-type material, and then you have increased your depletion region. So what next? What happens if we increase the gate potential? Logically, you will see an increase in the depletion region width, but if you see, this area is already depleted of its majority carriers. So how will be the there will be more amount of accumulation of the negative charge metals over here. So let's look into that. So when you increase your gate voltage even further, there is no source of negative charges which is present over here. When you increase your positive potential over here, it wants to attract more and more negative charges, or it wants to repel more and more positive charges, but there is no way it finds a positive charge over here, because this part of your MOSFET is depleted of its majority carriers, which is positively charged particles. So what happens now? So what happens is, if you see this N plus heavily doped source region, this particular gate area, this particular positive potential will now attract the negative charge particles from this N plus source area, because it's just like a magnet. Wherever it finds particles, it will just try to attract it from there. Okay, so when you increase your gate potential, there is no way that it can repel more positive charges, because it's already depleted of the positive charges. So it will attract the negative charges from the nearly spaced source area, which is heavily doped with N plus region. So it will attract it, and you see the channel width gets increased. So this is your channel width. The one which you see over here, that's your channel width. Your width gets increases, but there will be no change in the depletion layer width, and that's logically true, because this area is already depleted of its majority charge carriers, which is P-type materials. Okay, so there is no change in the depletion layer width, but there will be an increase in the channel width, and this is how the channel width increases. Let's have a close look over here. So if you see, the electrons are being drawn from the heavily doped source region, and the channel width increases. So just focus on this area. You see how the channel width increases, and there will be a point at which you see a continuous n-type channel from source to drain. Okay, so now there is a possibility of current flow, because you have a way, you have a bridge that gaps that basically covers the gap between source and drain. Initially, when there was no potential, the source to drain resistance was so high that there was absolutely zero current flow from source to drain. But now, because of the application of the gate to source voltage, you have a continuous source to drain channel that will allow amount of current flow. Okay, so at zero potential, at zero drain voltage and at zero source voltage, you see a very small amount of current, and we'll be talking more about that when we reach to sub threshold concept discussion. For now, we'll assume that there is no current unless and until we apply some potential. So there should be something that should pull electrons from this area to this area, and that will happen when you apply some potential at the drain area. We'll come to that. That is a different region of operation. Right now we are talking about a region of operation which is cutoff region. We are talking about cutoff region of operation. So there is a continuous channel now available. Now it's just the application of potential that will allow the current to flow from source to drain. But before concluding on the threshold voltage, we have to look into one more important parameter, which is the body terminal. So how does the body terminal plays a very important role in deciding the threshold voltage? We have talked about usually when you see a symbol of NMOS that represents this particular device, the substrate terminal is always connected to the ground. Okay, but that's not always true. That most of the time that is true. But in order to decide the threshold voltage equation, we have to do something with this particular body terminal and see what happens. So what we'll do is we'll take two scenarios. We'll take one scenario which is the original scenario where your VSB is 0. So basically, when you don't apply potential between the substrate between the source and the body, your VSB is 0. And we'll take another scenario where we are applying a potential between the source and the body. Okay, and that potential makes this basically we are giving a positive potential to the source and negative potential to the body. So in this case, if you try to calculate VSB, that's basically positive value. So when you apply a positive VSB to this particular terminal, what happens? What can happen? So the first thing that you see that you can directly see is this is a PN junction diode. So the depletion width over here, that will be more compared to what you see over here. If you see this particular depletion width and if you see this particular depletion layer width, this is more. And why is that? Because now this PN junction diode is more reverse bias. There is an additional reverse bias that is being applied to this PN junction diode, because you have this N-type material, N-type area which is connected to a positive source. You have the P-type substrate which is connected to a negative source. So there is an additional reverse bias on the top of the gate voltage. There is an additional reverse bias, and that basically increases the depletion width in this area. This region still remains constant because there is no additional potential over here, but over here you see an additional increase in the depletion layer width. Okay, because of the additional reverse bias that is being applied between source and the body. That is the first observation. Okay, that is the first observation. There is one more observation, that when you increase the gate to source voltage between over here and over here by the same amount, there is another phenomena that happens, that the inversion that happens at this point, that will be a bit delayed. Why it will be a bit delayed? Let's come to that point. So what I'll do is, since I'm running a bit late out of time and we need some few more minutes to discuss what happens when we apply the gate to source voltage, let's try to look into this particular phenomena. So basically, you increase the potential, you increase the gate to source voltage by the same level, and see and observe what happens in this scenario and what happens in this scenario. So we observed at a threshold voltage, at some threshold voltage or at some gate voltage, you happen to see you observe a strong inversion over here. So the question is, does at the same voltage, at the same gate to source voltage, does the surface inversion happens over here as well? So what is the answer for that? So let's try to answer these questions in the next video. Thank you.